And this is the time for the rest of you. Maybe you had some questions jotted down earlier that you didn't get to ask, or you just want to learn more about a particular area that somebody talked about. We're going to take a few minutes to just give you that opportunity to ask questions. And I want to make sure that there have been references made to people who are doing a lot of this work, being in the room, but there are also people who are new to the topic. We recognize that. So I want to make sure that everybody feels comfortable to ask a question, however basic, because all of it is important to the story. And so this is your chance to kind of dig in a little bit further. And there are people with microphones in the room that will come to you. The only request I have is just that you say your name and if you have an organizational affiliation, just so that our team can know how to direct their answer to you. So any takers? To start, yes.
Hi, I'm Inslee. I'm from Onset. We make the Hobo data loggers. This question is actually for Jim. You said something about how you guys are all scientists and you know this, and I am a scientist, but I don't know this. What is the relationship between salinity and methane that you were discussing?
Okay, so this concept kind of goes back to, I think, a 2011 paper by Hannah Poffenbarger, and she showed that about 14 parts per thousand salinity, which is kind of brackish. Was that right?
14 to 18.
Yeah, okay. That you get not just the salinity, but the sulfates that come with the salt, that can reduce methane production.
Can I add? Oh. So I think this is the coolest biogeochemistry stuff there is. So basically, you've got in salty water, you've got microbes that are sulfate reducers. They use that sulfate the way our bodies are using oxygen, right? And so when that sulfate is present, those microorganisms are able to outcompete the ones that are doing methanogenesis or methane production. And in fact, some of these microbes even switch between the methods potentially, but when sulfate is present, you get more energy out of reducing sulfate than you do out of creating methane. So it makes sense that they can outcompete and that that would be the preferred pathway. Then as that sulfate starts to decrease, as you get fresher and fresher, that methane pathway takes over. So this is why we keep harping on the methane piece and the salinity piece and better understanding all of those dynamics and what's controlling it where, because a slight change in salinity or potentially other conditions can suddenly turn your wetland into a major carbon sink, and then it can actually become a carbon source because the methane is such a stronger, more potent greenhouse gas. So hopefully that gets at your, what the heck is this salinity thing, methane? Yeah, it's totally cool.
We haven't specifically, and I would say that's generally a lack, right? Is once these systems are restored, there's not a lot of post-restoration monitoring. One, because there's probably no funds, but we haven't looked at ourselves, the benthic communities or anything like. We primarily focused on the carbon. So the plants transition really rapidly. At all of our youngest site was 3 years, and it had undergone full transition to Spartina species, but. I don't know.
Yeah, so it's true. We are not focused on those other ecological processes, but specifically with the Herring River, the Park Service, of course, is very closely focused on those, and the carbon is only one of their objectives in the restoration. And so they have quite a lot of data on fish passage and predicted changes in fish passage and other changes in the broad ecology and productivity of the system. But those portions are a little bit better known. People have been, of course, asking that question for a long time, since maybe the 1970s. What are the ecological consequences of tidal restriction and restoration? So they're better known than these carbon and greenhouse gas pieces are.
So for carbon, many people think carbon is like an indicator or the currency of the ecosystem function or ecosystem services. So when we measure carbon, of course, it comes with other ecosystem services. It's just carbon is one of the indicator to showing the strength and healthy of the ecosystems. Like in my group, for example, for the Hen River, we recently started to look at the crab density, feeder crab density associated with Spartina saltmarsh density. They are strongly correlated. So when we restore the saltmarsh, Spartina saltmarsh, they will come more with those feeder crab that come with other fishery density and biodiversity as well. I mean, there's many things come with that as a carbon buildup.
Yes. At the back.
Hi, good morning. My name is Abigail Archer, and I've been a volunteer in the Coastal Committee for the town of Brewster and Cape Cod. And so we have been looking at ways that we can preserve our wetlands for all the services that they provide, salt marsh. And in-layer deposition comes up as a topic, and normally if you talk about it, the first thing people say is, oh my God, the permitting. But I haven't heard so much about, is it effective? And then you've been talking about the small tweaks in biochemistry that can produce carbon source or sink. Are there examples of that being done successfully, and does it matter how it's done in terms of having carbon benefit?
So I can't answer that in the state of Massachusetts, but we had a conference in February that was looking at Chesapeake Bay marshes, and we had a couple speakers talk about this. And the answer to your questions is it matters a great deal. It can apparently be done quite effectively, and I would direct you to the Blackwater Marsh site, Wildlife Refuge in Maryland, where they have really effectively used it to help in a place where their marsh was really decreasing in elevation. That said, they had very specific conditions under which it was happening, and they pulled their sediments from an adjacent tidal creek, not from the main bay. So they had a lot of control over the consistency of the sediment, the fact that it was very similar to what was on the marsh surface. So everything I have heard about using sediments in other locations where you're bringing sediment from a deeper habitat, particularly where you've dredged it, so it's very effective, and it would be lovely if this just worked magically. There's a lot of caveats. You have to be really careful. My understanding is that it's very, very hard to deliver the right amount of sediment. In fact, the people who are doing that work kind of laugh when you say, well, we need about 2 millimeters. And they're like, yeah, you're just going to get what I can spew out there. So good luck with that, right? And it depends on how far you're trying to shoot it. Oftentimes you're trying to shoot it from a boat in the water. And so you're going to reach different parts of the marsh in different ways. It comes out very watery, so it's very hard to know what are you really getting. And in the worst case scenario, I have heard of a couple of examples where they put on so much that when it solidified at the end, it was like concrete, and they basically just fully covered and killed their marsh. And I've seen almost no data on how this affects anything up the trophic levels beyond plants. So I think it is still a huge need in terms of research. I don't want to poo-poo it because I think there could be ways of doing this well, but I think it's not as easy as, I've got a boatload of sediments, can I dump it on your marsh, and isn't this a good thing? No, we are not there, and I hear that sometimes, and it concerns me greatly given the extreme where it can be really, really bad.
And I will just say that we have another Neuroscience Collaborative funded project that our research coordinator, Megan, is she in the room? She's back hiding in the room, involving 8 research reserves experimenting with thin layer deposition, and she could tell you some more. But see, we're trying to do these topics that are really impactful for management decisions and putting what we learn out there. So this one will have even more than one reserve involved. So talk to Megan to learn some more about what they're learning from that. Any other questions? Yes? I see 2 back there.
Hi, I'm Kathy Wagner with the EPA, and I thought all the talks were excellent. Kevin, I just have a question about the conversion factor or model that you use for calculating the warming potential equivalents for the methane in your talk.
Yeah, thank you. Good question. So in addition to a significant amount of uncertainty and additional research needed on what the specific controls are on methane emission rates and what emission rates to expect under different conditions, there's also the question of how the methane behaves in the atmosphere once it's there in terms of affecting the climate. And the standard approach coming from the Intergovernmental Panel on Climate Change is to use something called a global warming potential. Those are a look at, usually over a 100-year time horizon, what's the climate impact of methane as a pound or a kilogram of methane in comparison to a pound or a kilogram of carbon dioxide. You can do that with other greenhouse gases as well. And so that's, in the past, it's been in the 20s. So with methane being, say, 21, it used to be, now 24, it's going up closer to 30 with revised modeling and revised estimates. In terms of the ratio of the warming potential of methane versus carbon dioxide. There's a problem with that approach, the standard approach, which is that they're based on modeling what the impact of that gas is on warming the climate if you have a single pulse release. So you model a pulse release of methane and a pulse release of carbon dioxide into the atmosphere. Their concentrations decline over time. Methane is removed from the atmosphere in about 12 years. Carbon dioxide, a lot of it is removed over a few decades, but then a significant portion of it remains for centuries in the atmosphere. So since it's a very short time frame for the methane, it shows up as a number in the 20s to 30. That's despite the fact that in terms of an instantaneous warming potential, it's closer to around 90 times more impactful than carbon dioxide is in terms of its ability to trap heat. So there's another approach. Instead of looking at a single pulse, you can model how much heat is trapped in the atmosphere if you have a continuous release of a gas. If you look at a wetland ecosystem, it does what it does year after year after year. So you have to model it on a longer time frame than just a single pulse. And so if you do that modeling, you find that the methane shows up as a sustained release as substantially more impactful in terms of trapping heat than the standard global warming potential. There was a paper by somebody named Scott Neubauer and Pat McGonigal a few years ago, in which they developed an idea which is called the sustained global warming potential. So you look at the ratio of methane to carbon dioxide in terms of trapping heat with a sustained emission or a sustained removal. And that number comes out to 45. And so in these calculations, what I used was that 45 sustained global warming potential. I've done the modeling as well in the past for some of these other publications that have been talked about, and it depends quite a lot on what time scale you look at. And a lot of what we need to do in terms of climate really is on a time scale shorter than a century. And we obviously have to think about what the climate's going to be several centuries from now, but we also want to take actions that have impact on shorter time scales than that. And if you look at the shorter time scales, methane is probably substantially more impactful than the sustained global warming potential of 45. But for now, using those published numbers, that's the number we used. The harder part, I think, is knowing what emissions to expect, what rate of methane emission to expect under a future scenario. We used a number that was slightly higher than the methane emission rate that Jim showed us for Phragmites, which was extremely high. We used a number that was slightly lower than what Jim used. But there's a lot of reason to think that the future methane emissions in a system like this will be quite high, because one of the controls besides salinity is water level. So if you have a very high water level, you have very little opportunity for oxygen penetration, and so you get a lot of methane emission. Also, we're expecting, of course, warmer temperatures, probably more productivity from the plants with some carbon dioxide fertilization. So collectively, we should expect pretty high emissions.
Thanks, Kevin.
So what's a policymaker to do? I mean, what number should we use?
For a global warming potential?
For methane. Like, support, the 20-year estimate for a conversion factor of like 88 to 90, or should we use 45 or 25?
Yeah, I would say it depends on the purpose. If you're going to do a national inventory or a state level inventory, if you're going to look at a carbon market project, well, there you're constrained by published protocols, right? And so you kind of have to use the standard global warming potential, whatever's in the protocol that you're going to apply. If you're doing research, I think it's pretty straightforward to do the radiative forcing modeling, and so I think that's the best approach. Second best would be to use a pre-calculated sustained global warming potential, the 45 number. If you're somewhere in between research and applying an inventory or a carbon market, I would say the sustained global warming potential is the best bet.
All right, let's take two more. I see one who's here, and then at the back, you had your hand up too, please.
Hi, Jeff Hughes from Wellesley College. Question for Jim Kang. I'm curious about the spatial variability of your measurements of gas fluxes in, say, a salt marsh. Do you replicate your measurements, and how do you choose the sites that you actually put the devices down?
Yeah, this is always issue. I mean, when we measure, we call sampling, right? We are sampling some location. For salt marsh, I think we're doing pretty good job. Usually we have many sites with the salt marsh, and each site usually we set 5 locations, spatial location, and then we sample them and we calculate the mean value across those spatial locations. I think the spatial uncertainty of the marsh itself for CO2 is pretty stable. We get a very good confidence, but for methane, that's uncertainty level is higher. Because methane is more related to, the from temporary point of view, it's called the bubbling, right? It's not, continuously released methane. Some point we get the bubbling process coming out. The other point is just stable. So the methane process or methane measurement is more complicated, both spatially and temporary. But CO2, yes, for the spatial pattern, when we measure, I think we have a confidence we capture the spatial variability.
Great.
Yeah, thank you.
At the back?
Yes, hi. I'm with the state, Massachusetts state government, and as states are thinking about ways to reach net zero goals and how to incorporate national working lands carbon into climate action plans. It seems like there's a lot of work that needs to be done on inventory. The types of wetlands and how those wetlands are emitting or low methane emitting or high methane emitting wetlands. Besides the inventorying issues, what other science questions, major science questions, need to be figured out before you, as scientists, recommend the state to go towards whether this is a statutory goal or an aspirational goal towards net carbon?
This mic's a hot potato.
Yeah. Well, that's a great bunch of questions, and I'm glad you're asking them. I guess, I think you hit on what some of the main tasks that are needed are. We do need much better, substantially improved maps. We need better spatial representation of not just where the wetlands are in a kind of a broad classification of, this one's impounded, this one's diked. We need functional maps that tell you about the condition of those wetlands, because the amount of greenhouse gas emission you might be getting from a wetland or the amount of benefit that you might get from restoring a wetland it's going to be variable across wetlands and depends a lot on conditions. We need much better data on the carbon cycle processes, what the actual methane emission rates are. Methane is particularly impactful. And we also do need to know something about what the future condition of these wetlands is going to be. If they're not restored, what's their condition going to be in a few decades or at the end of the century? Because that's the comparison we need to make. I've had conversations with people before, you know, at an agency, a federal agency. It was a candid conversation, very helpful. One of the comments was, we don't know that we necessarily want to do a lot more wetland restoration because there's the concept that they may not be there for very, very long anyway, right? And, you know, part of the response to that is we need to look forward and look at what kind of perhaps worse condition that coast is going to be in the future if we don't restore it. Not just at the negative side of that, the possible absence of the wetland in the future, but we need to know perhaps there's an even worse condition that might exist a few decades down the road if we don't restore it. So you don't want to compare what's it like now to what will it be like in the future if we restore it. The other thing is that we will have those wetlands. They will persist into the future if they're given that migration space. So we do need some future planning in terms of integrating wetland accommodations, migration accommodations with our infrastructure planning and development. There's obviously going to need to be a lot of new infrastructure development over the next several decades. And if we open up space, even with a high rate of sea level rise, we'll still have salt marshes. They'll just be farther inland.
I want to add that you've got 5 scientists up here, and of course our answer is always going to be we need more data, because that's what we're trained to do. We're trained to find an answer and then find what we still don't know, right? So I would actually, perfect answer by the way, but I would encourage you to not see it as what do we still need before we can take any kind of policy action, but instead, how could policy action potentially actually be facilitating everything Kevin just said? We should go for it, and we are going to make mistakes. But if we wait until we have the perfect data, we will be waiting forever, because there will always be more we don't know and that we want to know and that would be helpful. Sure, I mean, right? Yeah, absolutely. But we should go for it, and we should try things. I think setting an aspirational goal in particular at the state level would be amazing, and then to start funding projects, but to make sure that as part of that funding, as Megan said, there's monitoring funding as well. And then answer some of these questions that we don't know the answers to. And yeah, some of them may not end up being the sync we were hoping for, but we will then learn and figure out how the future project should be better. And without projects going into the ground where we can monitor all of this, we won't answer those questions that Kevin just laid out as easily, because we need those sites, we need to be trying things, and then we need to monitor what's working and what's not. So I'd say go for it, Massachusetts, be a leader. That would be incredible, but know that there will be things we learn along the way, which means everything won't go exactly as we hope it will. And that's okay, that's part of the process.
Thank you. And we're going to have one more, but see, that's why we brought Ariana and Kevin, so they could, and Han, thank you so much for that question. We'll take one more question, then we're going to switch gears.
This question is for James. My name is Acacia Warren, Environmental Genomics of Massachusetts. I'd like to represent the foreign community of scientists. Those of us that are looking for the United States to tell us, is it true that mangrove forests actually store more CO2 than any other ecosystem? Why we are not doing something about Florida, Gulf of Mexico states, to restore mangroves? Where can we find information about it?
So because mangroves have the woody biomass component as well as the soil carbon component, they really do shine when we're comparing these different coastal wetland communities. Seagrasses and different tidal marshes are doing a fabulous job of pumping carbon below ground, but they just don't have the same above ground or below ground woody biomass component. So there's kind of no way that mangroves don't outcompete them there, even though all 3 systems are highly productive and are pumping carbon below ground. So yeah, mangroves matter a great deal. We are doing stuff with our mangrove restoration. You may not hear as much about it as I might like, but there is mangrove restoration going on in Florida and in parts of the Gulf. There's actually a lot of science also going on with where should we be trying to restore mangroves versus with changes in climate, should we be aiming for a salt marsh community instead, even if it used to be mangrove, for example? And then we even have mangrove moving farther north up the Florida coast and into places in the Gulf it hasn't been before because of climate change. So there is stuff going on there. There's also cool mangrove work going on in the Caribbean. So it is happening, and there are some of our protected areas in Florida where this is happening. The Tampa Bay example of restoration of a lot of ecosystems, including mangroves and seagrasses, is an inspiration, if you don't know about that particular restoration, where they improved water quality by treating sewage that was running into the bay, and now have seen an incredible resurgence in a lot of ecosystems. Mangroves were a part of that, although seagrass is the main star there. So yeah, there is work going on. Do you want to add? Because I think the mangroves are clearly a hero here that we want to be thinking about, but there are fewer mangroves in the U.S. than other parts of the world. So that's partly why I think you don't hear us talking quite as much about mangroves.
Yeah, just exactly that. Yeah, you're right. Mangroves do store carbon faster than pretty much any other kind of ecosystem. Everything good that we've said about salt marshes today, that applies to mangroves, and even more so to mangroves. They're just incredibly important ecosystems. They'll grow volume and elevation very rapidly. They protect the coast even more. Incredibly important ecologically. They cover a larger part of the globe than salt marshes do. They're incredibly important. And so all of the processes that we talked about, the carbon market potential, the carbon inventory, the hydrological management that we talked about happening in salt marshes, all of that happens in mangroves as well. So you have drained mangrove areas, you have excavated mangrove areas developed, you have impoundments in mangrove areas. So those all produce greenhouse gas emissions, and if we improve our management of mangroves, we'll get those same kinds of benefits.
And for international-wide, I know.
It's on.
It's on. International-wide, yeah, there are a lot of research on mangrove and carbon. I know like Mexico and Panama, a lot of people are doing research on the mangrove and how they restore, how they store the carbon in the mangrove system, and people even put those anti-flux system in the mangrove forest and look at the carbon storage over there. And in Southeast Asia and in China, there's a lot of research ongoing to look at the mangrove and the carbon. And there's a publication over there, and like CCRC and Jane mentioned, there's a lot of data actually from mangrove side. Yeah.
Great. So we're going to wrap this portion of our Q&A, but I know you guys still have other comments and questions that you might want to shoot to the panelists here. And I just want to remind people that I know it's a full day of talks and presentations, but we did build in free networking reception at the end for continued conversations and collaborations. And it's not just that the food is important, it is, but it's really all that these conversations can lead to. Many projects start with just, chatting with someone over drinks or something like that. So I encourage you to stay if you can and really continue with the Q&A and conversation on these topics. So thank you very much for your presentations this morning.